fraction decomposition, which is the easiest section in this unit, which is kind of cool. We like that. Keep in mind that your worksheet is due this Thursday night by midnight. And that gives you some walkthroughs of some of the important concepts in this unit, trig sub being one of them. So let's go ahead and work on this one. Trig sub is going to be the substitution that we want to use here. And one of the indicators that trig sub is a good way to go is that we've got a difference of squares. And we can't use regular substitution. In order for regular substitution to work, the derivative of that quantity would have to be present, and it's not. So if there was an x up in this numerator, then regular substitution would work fine, because the derivative of x squared is 2x, and there's an x there. But there isn't that convenience, so trig sub, usually for a sum or difference of squares. Now, the way that I like to do these is to create a sum or difference of squares with a 1, a trailing 1, or a leading 1. You don't have to do it that way, but I find it easier in the long run. And if you think about years long run, it's a lot easier to remember an algebra technique than an integration formula with an a that's randomly placed in there somewhere. So in the long run, it's easier to understand how to do some algebra to make it a leading or trailing 1, and then you only have 3 things to remember: inverse sines, integral, inverse, the integral that goes to inverse sine, inverse tangent, or inverse secant. So you only have 3 things to remember in the long run. So I find that helpful. So I'm going to factor a 64 out of that square root. The power comes with the number that you're factoring out. So the power here is 1/2, so square root of 64 is 8. So that will be in the denominator. The 8 will be in the denominator. And inside here, when we factor out that 64, there is not a 64 here, so we put 1 in. And we want to rewrite that first term as a single square. And so that single square will be x divided by 8, quantity squared, minus 1. Now we have it set up. We've got a difference of squares with a trailing 1. And we can use trig sub here. And we have 3 choices: sine, secant, or tangent. Tangent goes with the plus, so it's sine or secant. And we ask ourselves, is sine squared minus 1 an identity?
Yes.
You might say, yeah, it's an identity, but what is sine squared minus 1 going to equal?
Oh. It's going to be a negative number.
Sine squared minus 1 would be negative cosine squared. That does not work. We do not want a negative square there. That's not going to be square rootable. So that's not the one. So we want to use the secant one. So we are going to let x divided by 8 equal secant of theta. And if you want to take the 8 and move it to the other side here before you take a derivative, if it's easier or whatever, if it's more obvious, you can do that. And then the derivative of secant is secant times tangent. Then we have our d theta. So that is our substitution. That allows us to take all of the x's that are inside that integral and turn them into thetas. So we will have 1/8 out in front. And we are changing to theta, so we're going to use some placeholder limits. We don't want to convert to theta right now. So the numerator is the dx. Well, dx is down here. 8 secant theta tangent theta. Down inside the root, we're going to have secant squared minus 1. And then a d theta. And that's our setup. We've now converted over to thetas. And I'll put that identity up here on the board again, just so you remember. So this is our secant tangent triangle. So when we look at that, we see, oh yeah, secant squared minus 1 is tan squared. So down here in the denominator, we're going to, oh, I can factor that 8 out, right? That 8 can factor out and cancel out that 1/8 out in front. So in the denominator, we have square root of tangent squared. And technically here we have to be careful. The square root of tangent squared is sometimes tangent and is sometimes negative tangent, depending on whether tangent's value is positive or negative. When we look, if we were to do a deep dive here, we can analyze whether that's true or not here. With this book, they're not going to try to trick us. There's enough going on already. I think there's one question where they do try to trick you, but in general, I'm not going to try to trick you. If you see the square root of tan squared, tangent. There's enough other stuff going on that worrying about domain is kind of unnecessary. And so what we see here is that this tangent is going to cancel with that tangent. Square root of tan squared is going to be tangent. And so that will cancel right out. So we have the integral of secant. And we've looked at the antiderivative for secant a few times already. And we know that that is natural log of absolute value of secant plus tangent. So natural log, absolute value, secant theta plus tangent of theta. All right, plus an integrate. Oh, no, not a constant. We have a definite integral. So we've got this evaluation symbol. All right, so now we've found our antiderivative. It's in terms of theta. We would like to go back to x's. And the way we get back to x's is to draw this triangle that's sitting in quadrant 1 that satisfies this substitution step. So we look at our substitution step. It says that secant of theta is x over 8. We draw this triangle the same way every time as if it's living in quadrant 1. Secant is hypotenuse divided by adjacent. So that is our triangle, two of the sides of the triangle. And then the missing side will be square root x squared minus 64. And so that's going to allow us to get back to x. Secant of theta is x divided by 8. Tangent of theta is rise over run. We're back to x limits, which are 8 square roots of 2 and 16. So now it's just a matter of plugging these in. Plug in the upper limit of 16. Let's see, 16 over 8 is 2. And then if we plug 16 into that square root, we get 16 squared, which is 256. 256 minus 64 256 minus 64. I'm not doing it in my head right now. Got a little bit of a headache. So square root of 192, is that a perfect square?
No.
Does it have a perfect square in it? Or is 192?
12, 8 root something?
So it's definitely 2 goes, yeah, somebody look this up because I'm not thinking great today. So that's
8 square root of 3.
8 square root of 3? Yeah. Thank you. Something had to go in there. So we'll go 8 square root of 3. All right, so that is going to give us 8 square root of 3 over 8. So that will be square root of 3. So square root of 3 in there. Let's just slide that over there. Okay, now, oh, actually now I see why it's 8 square root of 3. Okay. All right, now we have to plug in the lower limit and subtract. So we're going to have minus natural log of the absolute value of, plugging in 8 root 2 there. 8 root 2 divided by 8 gives us root 2. And then we're going to have some other crazy thing here. So what do we get there? When we square it, we get 64 times 2. And the way I'm going to think of that, 64 times 2, I'm going to factor out the 64, which will give us 8 times, I think, or is it? Oh, it's just going to be 8, right? Is that right? Right, so 8 root 2 squared is 64 times 2, which is 128. 128 is twice 64, so we end up with square root of 64. Everybody agree with that?
Wouldn't it be 1 though? Because it would be 8 over 8.
8 over 8 will be 1. You are correct. Thank you. Yeah, so this part, the square root part, everybody see that? That's 128 minus 64. Square root of 64 is 8. 8 over 8 is 1. Yeah, thank you. That worked out a little more simply than I expected. And then we can combine these into one natural log. And this natural log does not have to have an absolute value in it because everything in here is positive. Let's write the roots. Let's write it so it's kind of looking symmetric-y. All right, so that would be our final. Yeah. Ooh, the arithmetic. Any question on any step there? All right, let's go to another one of these. These things are a little complex. So here is kind of a combination of two different things. One thing that we've seen is that if you have a denominator that doesn't factor, you can complete the square. And so when we complete the square here, in order to create a perfect square trinomial, what constant do we need so that this part here is completed?
9.
So we take that coefficient of x, divide it by 2 and square it, we get a 9. So that's what we need here in order to complete the square. So we're going to have x squared minus 6x plus 9. And we can just take that 9 from this 34, leaving it 25. And so now that we've completed the square, we can factor it. And that's going to give us x minus 3 quantity squared plus 25. We're going to factor that 25 out to the front. in order to create a sum of squares with a trailing 1 here. And once again, there's no 25 right in here, but we can think of that so that we're factoring out this 25, and then we can write what's left as x minus 3 divided by 5, quantity squared, plus 1. So we have two techniques that will work from this stage going forward. What form is that integrand in as we're looking at it?
Tangent?
Inverse tangent,
Oh, yeah.
arctan. So we could actually integrate this directly with arctan and the reverse chain rule. Because that is an arctan form. It's not like there's a big set of parentheses with a power on it. It is an arctangent form instantly. So we could actually integrate directly right now. Let's just suppose we didn't notice that though, and we were going to go trig sub just because we didn't notice. Would we use sine, secant, or tangent? We'd use tangent because we have the plus. So, and let's just notice what happens here when we do this. So we're going to use this substitution. We'll take the derivative of both sides. On the left we have a line, so its derivative is the slope. On the right side we have secant squared of theta d theta. So there is our substitution, and let's see what that yields. So we have a 25th out in front. Dx is going to be 5 secant squared of theta d theta. Down below we get tan squared plus 1. And what is tan squared plus 1?
Secant squared.
That's secant squared. So these two cancel. Secant squared and this whole denominator. Right? The denominator becomes 1. Tan squared plus 1 is secant squared. So that all cancels. And the simplified integral is going to be the 5 factors out to the front. We get 1/5 integral of d theta. Well, the integral of d theta is just theta. So we end up with that. And from right here, we isolate theta by taking the inverse tangent of both sides. So theta is just the arctan of x minus 3 divided by 5. So we're done. So if you are doing trig sub on a quantity that you actually don't need it on because you could have integrated directly, it just all comes out in the wash. So if you learn your trig sub well, you actually don't even have to memorize those 3 inverse trig integrals, because it just comes out in the wash. You just need to know whether to choose sine, secant, or tangent. Now if we did it directly, from this stage right here, you could do this directly and say, oh, this is equal to 1/25th arctangent of what's in the parentheses divided by the derivative of what's in the parentheses. And the derivative of what's in the parentheses is 1/5. And dividing by 1/5 is the same as multiplying by 5, so you'd get 5/25ths, which is 1/5, and you get the exact same thing. Those things are the same. So if you notice that it's in arctan form, you could use arctan's antiderivative in conjunction with reverse chain rule. And you'll get the same thing. All right. So why don't you all try this one down here. Factor out the 2 first. You see a common factor of 2, factor that thing to the front. That's kind of a superfluous 2 in there. Let's just put that in the front. And then you all try it. Complete the square. And let's see where it goes. Any issues with the completing the square part? Does that come back? Divide by 2 and square to figure out what you need for that constant so that it's in perfect square trinomial form. Any questions? So I've got the completing the square part up, and then I wanted to create the trailing 1 situation, so I factored out a 9, and that pops to the front, multiplies by the 2. There's no power on the 9. It's not like we're in a square root or inside a power of whatever, anything. So it comes out straight up as a 9. This is in arctan form, so we could cut to the chase and integrate instantly. So let's do that this time. So we have 1/18 arctangent of the quantity u minus 3/3. And what would we divide by for the reverse chain rule? 1/3. The derivative of the inside here is 1/3. Right? That's 1/3 u minus 1. Its derivative is the slope, which is 1/3. So if we cut to the chase, we would end up getting this. All right, so that's how we would do it with the reverse chain rule. Again, if we didn't see that, we would choose tangent so because that's a plus there, we're going to let tangent be the inside, and the derivative of the left side is 1/3 du. The derivative of the right side is secant squared. And so let's go the other technique over here. So we're going to end up with 1/18. And then du is going to be 3 secant squared of theta times d theta, all divided by tan squared plus 1. And we have the same thing that we saw with the last example. The denominator is secant squared. Tan squared plus 1 is secant squared. So that and that cancel. So we end up with 1/6 integral of d theta. That gives us 1/6 theta plus c. And to solve for theta, we come up there and we see that theta is equal to inverse tangent of the other side. So we get inverse tangent of u minus 3 divided by 3 plus c. And those, of course, are the same. So if you see that you can integrate directly with an inverse trig function, you could do that. If you don't, you can just go straight to trig sub. As you get better at trig sub, that might be, it's pretty quick with trig sub on something like that. It's the best trig sub ones, the fastest ones. All right, any question on that? Okay, so let's go to partial fraction decomp, and we'll see how far we go. If we have time, I'll let you practice some more trig sub at the end of class after we get back from our break. So let's go to partial fraction decomp. This is the easiest part of this unit, so that's kind of nice. PFD is the shorthand for partial fraction decomposition. And what I want you to observe is a couple of things here. We've got a rational function over there, and that looks like a pretty complicated integral, right? We'd have to complete the square and basically do some stuff that allows us to manipulate that and maybe use u sub, maybe trig sub, who knows. But notice over here, these two things are equal. If you already know how to go this way, right? That's easy. You get a common denominator, you combine the numerators, right? You did that all through algebra, combining two rational functions to create a single denominator. But you've never gone that way. That is what PFD is. You want to build these so-called partial fractions from this bigger fraction. So you want to take your bigger fraction and break it apart. Because when you look down here, that's easy, right? Both of those terms are in log form. So this immediately can be integrated to the natural log of absolute x minus 2 plus 2 times the natural log of absolute value of x plus 4. Right? So if you were able to write this more complicated looking fraction as the sum of partial fractions, that's really easy to integrate. So this gives us another technique. But what's important to realize is that this technique is going to work if we can factor the denominator. And so we have to be able to factor the denominator. Not with completing the square, not that, but just regular old factoring, foiling. If we can do that, then notice that each of these linear factors are going to be over here in the denominators. So those partial fractions are going to be built as fractions with those denominators. So let's try it. Let's try PFD. So we have this horrible looking slide here that you really should look at for no more than 5 seconds because it'll give you a headache. Let me explain what they are talking about here. So we've got our rational function and we want to factor the denominator. And all they are saying is that if you factor your denominator into a bunch of little linear factors, then this is going to be the form of the PFD. You put a constant over each factor. So if we go back to our prior slide for a second, and we look here, once it was factored, we ended up with, we haven't talked about how you get the 1 and the 2, that'll come, but what you end up with is a constant over each of those linear factors. So if your denominator factors into a bunch of little linear factors, the form of your PFD is constant over linear factor, all the way through. So that's all that slide is saying. It looks way worse than what it really means. So that's what it says. And then we have to find these coefficients. So here's going to be our technique. And there are a couple of ways to solve for these constants. We'll talk about these 2 different methods. So we're going to take what's inside here. Now they already factored this for us. So we're taking the integrand. We see 2 linear factors. And they are going to form the denominators of our partial fraction decomp. And in the numerator, there will be a constant. So that's it. Now we're back to algebra. We need to solve this system for A and B. And our technique is to multiply both sides by the denominator on the left. If we multiply both sides by the left denominator, we're going to clear out all the fractions. So we're going to multiply both sides by, maybe I'll write it this way. So we're going to take this whole equation and we're going to multiply by that. So on the left, if we multiply by that, the denominator cancels. On the right, we have to distribute. So when this pair of factors comes over here, the x minus 2's are going to cancel. So we're going to have A multiplied by x plus 6 plus B When this pair of factors multiplies to this fraction, the x plus 6's cancel. So we end up with that as our simplified PFD equation. So here, we're going to do the traditional method of solving. There's two techniques right here. We're going to use the traditional method. So on the right-hand side, I'm going to distribute. And then just to be thorough, let's see. I'm going to rewrite the right-hand side like this. So I'm going to group together the two terms that have an x and then the constant terms. I'm going to just kind of pair them together. And if you wanted to, you could factor that x out and really write it like an mx plus b form. So it's a constant times x, and this over here is a constant. A and b are constants. So over here, 6a minus 2b, that's just a constant, right? Now, if I ask you this question, if I say, let's suppose we have ax squared plus bx plus c equals 4x squared minus x plus 1. Can you tell me what a has to be? 4. Tell me what b has to be?
-1.
-1. C has to be? 1. Correct. The only way two polynomials can be equal is if the corresponding coefficients are the same. Coefficient of x squared matches. Coefficient of x matches. Constant match. Well, on the left, we have a polynomial. This is 0x plus 8. On the right, we have a polynomial. So what this tells us is the coefficient of x right here must be equal to the coefficient of x over there. The constant over here must be equal to the constant over there. The only way two polynomials are equal is if corresponding coefficients match. So this builds a system for us. This tells us that 0 equals a plus b, 8 equals 6a minus 2b. So it builds this system of equations. And so back in algebra, you learned how to solve these systems, right? You can use substitution, you can use elimination, two different main techniques. I'm going to divide out the 2 in the bottom row just to clean it up because we can divide by 2. So there we have our reduced system. Looks very easy to solve this with elimination. If I add these two equations together, don't we eliminate the b? We have plus b minus b. So this tells us that a must be 1. How do we get b from a?
Solve for the first equation.
Yeah, we plug it back in. And you can plug it back into either equation. It doesn't matter. Plug it in here. A is 1. Subtract b is -1. So it doesn't matter. You can plug into either equation. And that's how you're going to get your second coefficient. If you plugged it in down here, you'd have 3. Subtract 3. You get 1 equals -b. So b will be -1. So you solve for 1 through elimination or substitution. back substitute it in, and you've got your second coefficient. So now we have the following. Let's, again, call this integral something just so I don't have to rewrite it again. We'll just call it omega. So our original integral can now be rewritten as the integral of a over x minus 2 plus b over x plus 6. So the original integral can be redone like that. Both of those fractions are in log form. Their derivatives are the numerator. So this will be natural log absolute x minus 2 minus natural log x plus 6 plus c. And we can combine these with a log property. And that log property says that if you're taking a difference, you can turn it into division. And that'll be our antiderivative. All right, any question on any of those steps? So this technique is pretty quick once you see it.
Why'd you call that integral up there omega? Or do you have to do that?
No, I just had no space to say equals here.
Okay.
You know, so instead of rewriting this whole integral again or drawing a big long arrow or something, just calling it something that makes it convenient to name it.
Gotcha.
So, not a bad technique. Not a bad technique. Let me just check one thing. I'm trying to remember if I didn't check this before class. Okay. All right, so what I want to do now is compare this traditional method. So we're going to see that this traditional method is very important to know because there's going to be certain cases where this convenient value method is not going to work. So let me show you what the convenient value method is first. So let's move this guy and use this convenient value method. So the convenient value method, in contrast to that method, the traditional method that gives you a system. Let's take this equation right here and put it down here. Doesn't want to do that. Oh, and there's not a right click down there. But I should be able to. So here's what the convenient value method process is. So this equation right here, we say to ourselves that this is true for all x. So that equation right there is going to be true for any x. That's our simplified PFD equation. We got rid of the denominators. We no longer have a domain issue. Like up here, you can't plug in x equals 2 here because you'd get division by 0. But as soon as we clear out those fractions, this equation, if you just glance at it, has no restriction on the domain, no restriction on the x values. It's going to be true for all x. In particular, it is true for x equals 2 and x equals negative 6. It's true for all x. So if it's true for all x, it's true for those two x's. And look at what these two x's do. If we plug in x equals 2 for all the x's that we see, we get the value for a instantly. we plug in the value of -6 for all the x's that we see, we get b instantly. When we plug in -6, this term goes away. The first term goes away. When we plug in 2, the second term goes away. That's fast. And this convenient value method works really well whenever you have linear factors. We are going to see that there are times where you have quadratic factors, and this method doesn't work as well. Because when you see this method, you're like, oh, well, why wouldn't we always do that? And it works great if you have, especially if you have distinct linear factors. But if you should know from algebra that when you're factoring, if you are a factoring ninja, every polynomial can be factored into linear and quadratic factors. Right? That's the fundamental theorem of algebra. The fundamental theorem of algebra says if you've got a polynomial and you've got integer coefficients, you can factor it into linears and irreducible quadratics. You don't have to have a cubic, right? Every cubic can factor into a quadratic and a linear. Sometimes those quadratics can keep factoring, and you have 3 linears if you started with a cubic. But sometimes you'll have quadratics that you can't factor unless you use complex numbers. Like x squared plus 1. That's an irreducible quadratic. It doesn't have any real zeros. So we are going to see that the convenient value method is less convenient if we end up with denominators that are squares. But if they're all linears, this method is the bomb. Super fast. All right, so let's try another one of these. So we've got this. The first step to even considering this technique is that the denominator has to be factored. And so when we look here, we see, okay, yeah, that one factors. Is that quadratic irreducible? Or can it be reduced? Can it be factored? What do you think? Can be factored, right? A difference of squares can be factored. A sum of squares cannot be factored. So difference of squares can be factored. So now we're in this situation where we have 3 distinct linear factors. So when we come to do our PFD, to build our PFD equation, we take our integrand, and the format of our PFD, we are going to put a constant over each and every one of these linear factors. So that's our PFD equation. And then we multiply both sides by the left denominator. Our goal is to clear fractions. So we're going to multiply both sides by that. And when you multiply it by that first fraction, you have an x that's going to cancel. And so you're left with a multiplied by x minus 1 times x plus 1. When you multiply it by the second fraction, the x minus 1's cancel. So you're left with b times x plus 1. And when you multiply it by the third, the x plus 1's cancel. And you're left with that. So there is our reduced PFD equation. We cleared the fractions. So any questions up to that state? So we factored, We built our structure, constant over each factor, multiply by the denominator on the left, that clears out all the fractions. There we go. If we were going to go traditional method, we would have to expand all that, group the x's together, group the constants together. We don't need to do that. Let's go convenient value. So if we go convenient value, what are the three values of x that we're going to choose as our convenient values?
0, 1, and negative 1.
100%. So those are the convenient values. And I think you see why. Because they cause a bunch of zeros. They zero out those factors. So now we take this convenient value and we replace it with all the x's. So I plug in 0. On the left, we have negative 2. On the right, when we plug in 0, we get negative a right there. And what are the other two terms going to be with an x equals 0?
0.
0. If we plug in 0 right there and 0 right there, those two terms are gone. They vanish. Now we plug in the 1 all the way across. Plugging in a 1 on the left, we get 4 minus 2, which is positive 2. Plugging in 1 on the right. Oh, well, this is going to be gone, and that's going to be... And this one's going to be gone. Because if you plug in x equals 1, those two terms vanish. They become 0. So plugging in 1 right here gives us 2b. Now we plug in negative 1. Negative 1 on the left is going to give negative 4 minus 2, which is negative 6. On the right, negative 1, that's going to be gone right there, and that's going to be gone right there. And the only term that's not 0, let's see, we're plugging in negative 1 right here. So we're going to have negative 2 times negative 1, which is positive 2, times c. So positive 2 times c. And wow, yeah, that is convenient. We end up with a equals 2. We end up with b equals 1. And we end up with c equals negative 3. So we get to those values quite quickly with the convenient value method. So that allows us, this time I have space, I don't need to go with that omega thing. This just tells us that this integral now becomes the integral of 2 divided by x plus 1 divided by x minus 1 minus 3 divided by x plus 1 dx. All of those are in log form. So we can cut to the chase really nicely. 2 natural log absolute value of x plus natural log of x minus 1 minus 3 natural log of x plus 1 plus c. And if you want it to be, like a log, if you wanted to, you could bring those coefficients up as powers and combine the logs. I will not ask you to use log properties after you integrate with these. That's totally fine right there. But you could, bring this 2 up as a square, bring that 3 up as a cube, and turn it into 1 log. We don't need to do that. You can leave it as an expanded log thing. All right, any any questions on linear factors in the denominator? So the prerequisite for this technique is that this denominator needs to factor, all right? So these denominators have to factor. That's a little different. That last example that we did with trigonometric substitution, the denominator did not factor. So we used that completing the square technique. So they have to factor. All right, so We're going to up the ante just a little bit. We still are going to have linear factors only, no irreducible quadratics yet. And notice this, that if we have a repeated factor, we have to have a partial fraction for each power of that repeated factor. All right, so when we look down here, our PFD equation, we already have the denominator factored here. This is, just note, that's linear, and this is linear. So this, on the right here, is a repeated linear factor. That's not a quadratic factor. A quadratic factor is like x squared plus 1, right? Not a quantity squared. So this is a linear factor that's repeated, not a quadratic factor. So this, the form will be this. So certainly we have the a over x minus 6. That's a linear factor. Anytime we have a linear factor, the numerator is always a constant, even if that linear factor is repeated. So now we need a partial fraction for each power of that repeated factor. So we need a partial fraction for x plus 2, but moreover, we also need a partial fraction for that extra power on that linear factor. And if this thing was a cube down there, you would have a d over x plus 2 quantity cubed. So every power has to have its own partial fraction. So that is our setup right there. And we're still going to do what we did before. We take our PFD equation and we simplify it by multiplying by the denominator on the left. So that whole denominator gets multiplied all the way across. When it gets multiplied by this first fraction, the x minus 6's cancel, and we're left with that. When we multiply it by the second fraction, one of the x plus 2's cancel. And when we multiply it by the third, the x plus 2 squareds cancel, and we have c times x minus 6. So there is our PFD equation simplified. Simplified PFD. If we use the traditional method here, we would have to FOIL all this out, match the coefficients of x squared, match the coefficients of x, match the constants. I'm going to go with the convenient value method, and I've got to point one thing out to you. What are the two obvious convenient values?
6 and -2.
So we look at the zeros, we get -2, we get 6. You should know from algebra, though, that if we have 3 unknowns, how many equations do you need? 3. All right, so these are the two convenient values. Let's write down the corresponding equations for them, and then we're going to talk for a moment. So if we plug in x equals -2 on the left, we get 4 times 16, which is 64. And when we plug in -2 on the right, that's gone and that's gone. -2 plus 2 is 0 in both those. So plugging in -2 over here is going to give -8c. -8c. Oh, great. This tells us that c is -8. So we've already solved for one of our letters. When we plug in 6, On the left, we are going to have 16 times 36. We'll deal with that in a moment. On the right, when we plug in 6, second and third terms are both gone because we have a 6 minus 6 in each of them. And when we plug in 6 to the first, we end up with 64a. Do we agree? Plug in a 6, 6 plus 2 is 8, 8 squared is 64. So we can do a little simplification here. 16 goes into there 1 time, 16 goes into there 4 times. Divide the 4 and we get that a is equal to 9. All right. So we've got A and C, but not B. Here's what we can do. There's 2 things we can do. The easiest thing is to pick another value for x to create this third equation that's convenient-ish. It's not going to create a bunch of zeros, because we only have 2 that create 0 and we already used them. But when we look at this equation here, we want to pick a number that's really easy to substitute in. What number is really easy to substitute in when you have a bunch of x's?
0.
0. That's a great one. The left-hand side becomes 0. Let's see what the right-hand side becomes. So plugging in 0, we get 4a. Plugging in 0 here, we're going to get negative 12b. Plugging in 0 here, we get negative 6c. What do you think we're going to do?
So plug in C and A.
Plug in C and A. Plug in C and A and isolate B. So C and A. So we're going to plug in, let me write that out just to make sure you're seeing that. So that's 4 times 9 minus 12B minus 6 times C, which is negative 8. So what will be equal? I guess we could have canceled out a 2 up here beforehand, but we didn't. So it's just 36 minus, actually, let's put the 12b on the left side. 12b, 36 plus 48. If we divide by 12, we're going to get 3 plus 4, so we get 7. So there's our third one. All right, so let's just finish this thing off. So 7 is b. So that allows us to rewrite this as the integral of a, which we found to be 9. So 9 over x minus 6. B we found to be 7. So plus 7 over x plus 2. And then C we found to be negative 8. So neg 8 over x plus 2 quantity squared. The first two, super easy. 9, natural log absolute x minus 6, plus 7, natural log absolute x plus 2. How do you integrate that third one? What will we do to integrate that? How can you rewrite that so it looks easy to integrate? How are you going to rewrite that? What are we going to do with that x plus 2 in the denominator? Pull it up to the numerator? If we pull it up to the numerator, we just use the power rule. Add 1, divide by the new exponent, and then reverse chain rule if we have to. So the integral here, add 1 to the exponent, and we get negative 1, and then we divide by negative 1. So it's going to be plus 8 over x plus 2 plus c. That'll be our final answer. Everyone see that? Add 1 to the exponent, get a -1, divide by -1 makes the coefficient positive. And then you have x plus 2 to the -1, which means reciprocal of x plus 2. All right, let's go ahead and take a break. Take 10. Take 10. Contemplate things. Yeah. Let me hit pause on this real quick, and then we'll get back to that. All right. Let's see. I think we still have one more on this slide. All right. So let's do one more of these repeated factors. So we look in the denominator here, and we first acknowledge that this is a linear factor. That's not a cubic factor. That's a linear factor that's repeated 3 times. So remember, we're going to need a partial fraction for each power of that linear factor. So when we create our form here, our form will be a over x minus 2. So that's the linear factor to the first power. And then we have to have a second partial fraction for that linear power to the second power. And then a third partial fraction for that linear factor raised to the third power. Once again, we're going to simplify our PFD equation by multiplying through by the denominator on the left. So when we multiply both sides by that left denominator, so we're multiplying everything by this quantity right there. That's being sent across to everything on the right. So it multiplies to this one. One of the x minus 2's will cancel, leaving a pair. Multiply it by the second fraction. 2 of the x minus 2's cancel. When we multiply it by the third term, all we're left with is c. So there we go. We have 3 unknowns. And if we have 3 unknowns, we're going to need 3 equations. So given the fact that we only have one true convenient value, we have a couple of choices, right? The only convenient value is 2. So we would have to come up with 2 convenient-ish values, like 0 or whatever. We can also do a hybrid. We can do a combination of convenient value and then go to the traditional method. Let's do that this time just to change it up. So we're going to do one convenient value. So convenient value, the only true convenient value is 2. That's going to build the following equation. Oh, that was easy. So we've got one of our constants solved for. So here's what we're going to do. We are going to plug this back in, right there. Plug it back in, and when we plug it back in, we are going to then move it to the left. The only thing on the right should be stuff with unknowns. The c is now known, so we're going to move it to the left. And we're going to multiply out everything that's left on the right. So it's going to take 1 minute. Just multiply everything out. So the traditional method, this is what we need to do, multiply it all out. And on the left-hand side, let me write this suggestively, like that. So the traditional method says you've got two polynomials, the corresponding coefficients have to match. Let's do it. What is the coefficient of x squared on the left? 1. Now we come to the right. What is the coefficient of x squared on the right? A. Oh, we just got our second. So we know that A is 1. All right, we're almost there. What is the coefficient of x on the left?
0.
Huh? And then I'm going to come over here and I'm going to underline both the terms that have an x there. So on the left we have 0. On the right we would have negative 4a plus b. Oh, that's enough. We don't even need another equation, right? Because we know that a is 1, so what does that make b?
5, 4.
So if a is 1, we add 4 to that side, so we get the b is 4. Now we have all of our coefficients solved for. Now there is a third equation here that we could use too. Right? We've got that, and then we have these constants right here. So you could, maybe you didn't start solving and realize, you could say, oh, well, on the left is a negative 4 for the constant. On the right, you would say, let's see, 4a minus 2b. Same thing, right? If you plug in the a equals 1 here, you get 4. You subtract it to that side, you get negative 8. You divide by negative 2, you get b equals 4. So it turns out we don't need that third equation. 2 is enough. But if you did put it down, it would end up with the same thing. You would get to that. All right, so 1, 4, 4. So this will be equal to the integral. Which one was 1? A is 1. So 1 4 so we have that. The first term, log form, of. And what do you think we do with the second two?
Reduce.
Move them upstairs and then use the power rule. So let's rewrite this once more and then we'll do the integration. We'll just leave this thing lingering for a second. So we'll write this as, and if you can see this ahead of time, you know, maybe when you're writing this, you could say, oh yeah, there's a constant up there. Let's just move it up right, right out of the gate. So now it's in an integrable form. And so our first one, natural log, absolute denominator. Let's get our coefficients right here. Let's see. Add 1 to the exponent. We get a negative 1. Divide by that negative exponent. So we're going to get negative 4. And that's going to be a negative 1 exponent on the x minus 2. So we could just do that. And then over here, we add 1, we get negative 2. Dividing by negative 2 is going to give us a negative 2. So we added 1 to the exponent, we ended up with a negative 2. And if we just move that into the denominator to make that exponent positive, we always prefer positive exponents. we have that. Now, none of these required reverse chain rule. Just remember that we also have reverse chain rule if these were not just x's. If that was a 3x, you'd have to divide by 3. If that was a 5x, you'd have to divide by 5. So don't forget, reverse chain rule is kind of obscured here. All right, any questions on any of the steps there or the process? So here we did the hybrid approach where we did one convenient value and then we went to traditional. You could pick two other equations that were convenient-ish. You could pick x equals 0 and x equals 1.
That's what I was gonna ask.
Yeah. So if I was doing this with all convenient value method, picking 0 is an obvious candidate, and then picking 1, something that's super easy here, or a 3 even is a good one, because 3 minus 2 would be 1 for both of those. So whatever 2 you want to pick, you could. Okay. Let's get to the quadratics. So here is the only difference. You've got an irreducible quadratic in the denominator. That's irreducible. So irreducible quadratic. Notice the numerator is not a constant anymore. We want each of these fractions to be sort of a proper fraction. So if the denominator is linear, you can only have a constant in the numerator. If the numerator were linear also, then you don't have a proper fraction anymore. Proper, the power on the top has to be less than the power on the bottom. So we're sort of thinking about the most general proper fraction here. If the bottom's a quadratic, the biggest the numerator could be and still have a proper fraction is linear. So we're going to make that linear. So that's the only difference. So let's try one. So right here, we take our guts, take our integrand. Oh, there's a linear factor, right? X, that's a linear factor. And now here's a quadratic factor. How do you know if a quadratic factor is irreducible? Because if you say to yourself it's not factorable, it might just be that you didn't find the factors, right? So there is an algebra technique that will tell us for sure if it's factorable or not.
Quadratic equation.
So if we look at the discriminant of the quadratic equation, if we look at the b squared minus 4ac, the b squared minus 4ac being negative is what would blow it all up. Then you'd have an imaginary 0. So if we look at b squared minus 4ac, so we look in here, b squared minus 4ac, just to confirm. So remember it's abc, so b squared is 4. Minus 4 times a in this case is 1, c in this case is 2. We get 4 minus 8, which is negative 4. So that's what tells us for sure that that quadratic is irreducible. So so I'm going to call that D for discriminant. D less than 0 means irreducible. Okay. So let's go. Say again?
Oh, wouldn't it be easiest to just split the fraction here? Just take off one of the x's, under 3x.
Say that again?
Like x squared plus 2x plus 2 plus x over, you know, like split it into two fractions, and then you can just cancel out the, no?
I think you have an algebra thing going on, So because this denominator is all multiplied together, if we were to split the fraction, we would have to put it into each one of those. Like there's no cancellation because there's no x with this 2. Right, there's not an x here that we could then factor out and wipe out somehow.
Right, but what I'm saying is if we factor like x squared plus 2x plus x plus 2.
Oh, if
then
we
you could split
factor
it
the
into-
numerator?
Yeah, then you could just split it into 2 fractions.
So
but
then
cancel out
so if you factor the numerator, you'd split it into 2 multiplicative fractions, not 2 additive fractions. You know what I mean?
Okay, I see.
Like if you have a times b over c, when you're multiplying in the numerator, this c just goes into one of them. You could make this a over c times b, or you could make it a times b over c, but you can't do that. You can't integrate a product as a product of integrals. So you could turn it into a multiplicative thing, but it's not going to be advantageous.
Okay.
If we can turn it into a sum, then you can distribute the integral.
Well, that's kind of what I meant. I mean, maybe I'm not explaining it very well, but if we split it up so that the numerator is x squared plus 2x plus 2, and then the plus one where the numerator is x. No. I mean split it into 2 fractions. So x squared plus 2x plus 2 over the denominator.
Over that whole denominator.
Yes, plus x over. Then on the left, then you'll just have 1 over x, and on the right, you'll just have 1 over x squared plus 2x plus 2.
Yeah, you're still going to be in the same boat. Except you're going to have to do partial fractions twice then. This will still require proper partial fraction decomp. So when you cancel out these x's, you're going to have this right here. Well, I guess that is, that's not factorable. You would have to do partial fraction decomp anyway with that. And with this one, yeah, I see that would cancel, so you'd have a 1 over x. You would still have to do partial decomp, though.
Okay.
You'd have to do PFD.
Yeah, okay.
Yeah.
Fair enough.
But no, it's a good, absolute good thought, though, for sure. You still are going to have to do it at least once, anyway. Okay, so what we're going to do is say linear. So that takes care of the x. This actually is going to sort of end up with what you suggested anyway in many ways. So here, and that's a good recognition. It didn't even occur to me looking at this numerator, if you pulled off an x, that it would actually match that factor. That's good insight. Yeah. And it's going to sort of end up being, I think, the same anyway. You certainly could do it that way and see if it's faster or not, because that will work. Okay, so now we have that. Multiply, we have to get our simplified PFD equation. Let's see, where the heck am I going to put it? Let's just keep going this way. So we multiply both sides by the left side's denominator. So if we multiply the left side's denominator all the way through, we're going to end up with a multiplied by the quadratic factor. And then when it multiplies by this, the quadratic factors cancel. We'll have bx plus c multiplied by x. So there's our simplified PFD equation. Now, we could try to do a hybrid model here, but whenever there's an irreducible quadratic, you're going to have to use, you don't have to, you could create a more complicated system, but usually with an irreducible quadratic, at some stage you're going to want to do traditional method at some stage with that irreducible quadratic. So I think it's just easier to go for that right away. Let's just not try to do a hybrid thing. Let's just multiply this all out and go with the traditional method. So that we have that. And let's set up our system. So we have x squared, and x squared. So the coefficient of x squared on the left is 1. Coefficient of x squared on the right is a plus b. If we look at the coefficient of x, let's see, I see two terms on the right. So on the left, I see a 3 as the coefficient of x. On the right, I see 2a plus c. And then let's go for the constant. On the left, I see, whoa, just that and that. Okay, one term on each side. That's not too bad. So 2 equals 2a. I guess I didn't need to move this c over there. Keep it tight. All right, so what we see here is that a is 1. Oh, that solves everything for us, actually. If a is 1, then c is 1. And if a is 1, then b is 0. So that tells us then that we have, so a divided by x, so 1 over x, plus b is 0, so then x squared plus 2x plus 2. So we have that. All right. So, interesting. How are we going to integrate that bottom one then? The second one. What do you think? So that one's not factorable. So what did we do when we had a quadratic that was not factorable in the denominator?
Complete the square.
Complete the square. If we had a quadratic that was not factorable, we completed the square. So that will give us integral of 1 over x, which we know how to do that. So this is going to be x plus 1 squared plus 1. Everyone agree with that? We need to pull off a 1 here. So x squared plus 2x plus 1 is x plus 1 quantity squared, and there's 1 left over. And what form is that one in? Tan inverse? So this will be natural log absolute value of x plus inverse tangent of x plus 1 divided by the derivative of x plus 1, which is just 1, and then plus c. Yeah, and that kind of ends up exactly where you. Yeah, no, you had good insight actually.
Well, I mean, you got to show all the math so that we know how to do it.
Yeah, yeah. No, now that I'm thinking about what you were looking at, if you did that, we would end up with the same integrals. Yeah, yeah, yeah. Okay. Now here's a miserable case. Oh, before we do that miserable case, let's just talk about another possible miserable case. If this quadratic, irreducible factor were then repeated, you would have to have a partial fraction for each power of that irreducible quadratic. So if there was a 2 up here, then we would have to come down here and have a dx plus e over x squared plus 2x plus 2 squared. We would have to have a partial fraction let's actually do just a setup of one of those. Just, let's come down here. Just so that you have an example of it. So let's just suppose we had something ridiculous like that. So we have it cubed. This would be, so if I asked you just for the setup, I would never ask you to actually do this because it would be a nightmare. But I could ask you for the setup. So our first one is this. So irreducible quadratic, sum of squares, can't factor it. So there's our first partial fraction. Our second one would be cx plus d over x squared plus 1 squared. And then ex plus f over cubed. So that would be the setup if we had repeated irreducible quadratic. Yuck. You'd have to have 6 equations. So that'd be brutal. We'll not give that to you. All right. But let's try this one where we have 2. Let's see if this one's as bad as it looks. Okay, so it's already factored, and everyone's clear that these are both irreducible quadratics. All right, sums of squares you cannot factor unless you have imaginary numbers. Sums of squares. So those are irreducible. So what we're going to do is say, take the inside. And we would have an ax plus b divided by the first irreducible quadratic, and then a cx plus d over the second irreducible quadratic. And then, same thing we always do, multiply both sides by the left denominator. So we're going to end up with ax plus b times y squared plus 2 plus cx plus d multiplied by y squared plus 1. And definitely with no linear factors, we will not be using convenient value method. So we definitely will need to multiply this all out. Oh, what letter should I be using on the right?
Y.
Y. Too used to using X always. So we have to use the same letter, of course. So our PFD equation simplified. Now we have to expand our PFD equation. So we're going to have ay cubed plus by squared plus 2a times y plus 2b and then FOIL this one, we get cy cubed plus dy squared plus cy plus d. So there's our PFD equation. All right, let's see what kind of system this builds. So we're going to, let's look at maybe we'll put in some placeholders on the left just to be a little clearer. So, do we need to? Yeah, let's not do it. We're good. What is the coefficient of y cubed on the left? 0. So let's see, hopefully you can squeeze it in right there. So 0, so y cubed on the left is 0. And then on the right, looking at the y cubes, a plus c. Okay. Coefficient of y squared on the left.
B plus D.
0.
0 on the left.
Yeah.
And then on the right, let's just look at our squares. Okay, I think I heard a b plus d. Look at that. And then coefficient of y on the left.
0.
0. And then we come over here, look at y's on the right. There's a y, there's a y. So 2a plus c. And then our last one, constant on the left, constant on the right is there and there. So it looks like 1 equals 2b plus d. So, if we take these two equations and subtract them, you can do equation 3 minus equation 2, equation 3 minus equation 1, that gives us, so 3 minus 1, 0 minus 0, 2a minus a is a, c minus c is 0, and if a is 0, what is c equal to?
0.
Also 0. Okay. Then let's come down here and do those ones. It looks like if we do 4 minus 2, so equation 4 minus equation 2, so 4 minus 2, 1 minus 0 is 1, 2b minus b is b, d minus d is 0, so that gives us b is equal to 1, which makes d negative 1. Everyone okay with that? All right, cool. We've got some zeros. So A and, oh gosh, the ones that are 0 are these ones. So that's going to go away and that's going to go away. When we plug in the zeros, that's not going to be too bad. It looked worse than it was going to be. So we have integral of b over y squared plus 1 plus d, which is minus 1 over y squared plus 2. dy. First one's ob, arctan of y. Second one, if I want to put it in arctangent form, we want to have a trailing 1 there. So I'm going to factor out a 2 in the denominator. And when I factor out that 2, we're going to have a trailing 1. What is going to be there? When we factor out this 2 that's not there now,
Y squared over 2.
y squared over 2, and if we write that y squared over 2 as a single square,
Y over root 2.
y over root 2, right? We talked about that weird scenario if that thing was not, maybe it was Stockton, did you ask that question? If it's not a perfect square? Somebody asked that question.
Yeah, I did ask that question.
So we'd have that. And now it's in arctan form. So we're going to have arctangent of y minus 1/2. I'm going to leave a little gap there. Maybe I don't even need the gap. So for the reverse chain rule piece. So it's 1/2. It's going to be arctangent of y divided by square root of 2 divided by the derivative of y over square root of 2. And what is the derivative of y over the square root of 2? 1 over square root of 2, and we're dividing by it, so it becomes multiplication by square root of 2. So it's going to put a root 2 in this numerator right here. I guess we don't need that little dot there. We blast it out. So there is our antiderivative.
And the inverse one. The negative.
Thank you. Yes. Inverse tan. Thank you. Ah. All right, any step in this process that you are left with some questions on? Does it feel fair? It's very procedural. So it's one of those things that's kind of cool. Trigonometric substitution is procedural but very abstract. All right, so you all try this one. So here we have, well, I'm not going to even summarize it. You do this one. See if you can piece it together. So find the area of that shapely region. It's got a weird shape on top. It's not a polygon. Got to use integration. Whenever that denominator is factored like that, that's what sort of clues us into PFD. So PFD, the main strategy is to deal with a factored denominator. And in this case, that denominator, we've got an irreducible quadratic and a linear. Not here. Gael. Kim. Marcus. Ethan's here. Sean is here. Hayden here. Alexander's here. Shay not here. Stockton not here. Oh, I put a check. Nathan not here. Mason's here. Maxwell's here. Caleb's here. Sebastian was here. Garrett, MIA. Tura's here. Eric was here. Jesse here. Will here. Tyson not here. not so convinced of this strategy of not coming to class. The data is very clear. Is there any question on the PFD setup there? We have one linear factor and one irreducible quadratic, so we're going to have the linear factor with a constant in the numerator and the quadratic factor with a linear in the numerator. And we're going to go with the traditional method. So whenever we go with the traditional method, it's easiest just to multiply everything out. So we end up with that. And the traditional method just uses that basic concept that if you have two polynomials, the only way they can be equal is if the corresponding coefficients are the same. And so I'm going to look across here, and I'm going to look at the quadratics first. So -1 on the left, a plus b on the right. And then we'll look at the x, so the linear. 1 on the left for the linear, c plus b on the right. And then constant. Constant of 0 on the left and a plus c on the right. Yeah, question?
Do we gotta plug in x equals square root of -1 because that's also 0?
No. So we're only looking at real zeros here. So if we have an irreducible quadratic, we can't go with the convenient value method because the 0 is imaginary. So I've never tried to do that. It would be interesting to see what happens if you have free time. So yeah, we'll just go with the traditional method where we set the equations equal to each other, match the coefficients, and then we end up with this system. And we don't have what we had in the last few where you could just sort of do a pair of equations and solve for one of them. Here we're going to have to create a secondary. We're going to have to do a simplification by, we see the bottom equation is a plus c. It has an a and a c. And with the top one here, I'm going to combine these equations by eliminating b. And then I'll have another equation with a and c. So I'm going to do equation 2 minus equation 1 to get this new system here. So 1 minus minus 1 is 2, c minus a, and then b minus b is 0. Now we've got a system that we can solve pretty easily. If I add these two together, we'll get 2 equals, let's see, minus a and a cancel, and 2c. So we're going to get c is 1. And that tells us if c is 1, then a is -1. And what does that make b?
-1.
Oh,
wait,
Zero.
sorry.
0. Thank you. Yeah, 0. I'm seeing 0. So there are the 3. So let's see. So I'm just going to use this as a marker in my head. So b is 0, so that one's going to go away. So c is +1, a is -1. All right, a is -1. So this is going to be -1 over x plus 1. And then c is +1 over x squared plus 1 dx. Limits of integration 0 to 1. Does that look Like what you got, hopefully. This is pretty direct, this integration. We'll get minus natural log absolute x plus 1 plus the inverse tangent of x, interval 0 to 1. Zero, non-contributor. We like that. It's going to be 0 in both cases. Natural log of 1 is 0, and inverse tangent of 0 is 0. So we only have to worry about the upper limit of integration. So minus natural log of 2 plus inverse tangent of 1. Inverse tangent of 1, angle on the right with a tangent value of 1.
Pi over 4.
Pi over 4. So minus natural log of 2 plus pi divided by 4. And that's as far as we can go. That area seems pretty tiny. Oh yeah, that only goes up to less than 0.2. Okay, so I say that seems very little. Someone want to type that in just to get an approximation out of curiosity? Feels like it should be about a 1/10. Pi over 4 minus natural log of 2.
0.092.
0.092. Yeah. Small. Small area. All right, let's go do our last one for 8.5. Got this hanging cable-ish looking thing. It's not a hyperbolic cosine though, it's that with those. And we're going to rotate, let's see, so what does it say? So we've got that thing. Y equals 0 is the x-axis, x equals -1, x equals 1, rotated around the x-axis. So that whole region is going to be rotated around the x-axis, creating kind of like a sideways spool-looking thing. So we're going around the x-axis. The natural choice would be to use disk, washer, or shell. Disk. So the natural element would be a vertical element. Horizontal element makes no sense because if you drew it right up here, it would bounce into that curve right there. So that'd be a pain. And then you'd have to isolate x for that thing. You don't want to go there. So this is going to rotate around. It's going to create our disk, representative disk. We're going to integrate all the way across. Or we could integrate from 0 over to 1 and double it using some symmetry. So the volume, well, let's do the area first. Area of a disk is pi times the radius squared. So it's going to be pi times the radius is given by the function. So we're going to take that function, 1 over the square root of 4 minus x squared, and then square it. So that is going to be the area of the disk at x. And then the volume will be the integral from, let's double it. So we're going to say volume will be 2 times the integral from 0 to 1 of the area. That's going to be pi divided by 4 minus x squared. Wow, that all simplified pretty nicely. So we get that. So we'll factor out, well, actually, we're in the, so we have 2 choices here, actually. We could see that there's a difference of squares in the bottom, and we could use trig sub Anytime we have a difference of squares, trig sub's a good candidate. But that factors also into two linear factors. And we're in the PFD section, so let's do it that way. So what I'm going to do is factor out the negative sign from the bottom and the pi from the top. And factoring out the negative sign from the bottom, we'll put it in descending order. That's way easier to deal with. So we're going to have negative 2 pi, and our factorization, difference of squares. So I'll have that. So then we'll come over here and do our PFD business. Yeah, we love these PFDs with linears. PFD with linear. So we have that. Convenient value or traditional? We got two linears, so might as well go convenient value. Yeah, that's going to be a little quicker. So our two convenient values are x equals negative 2 and 2. We'll do that. So we got plug in negative 2 across the board, and I am seeing that equation. If I plug in a 2 across the board, I am seeing that equation. So B, negative 1/4, and A, positive 1/4. All right, so that tells us. Any issues with that? With that PFD business? Seems pretty straightforward. All right, so then we have negative 2 pi. This is going to be the integral, 0 to 1. We're rewriting. We have a 1/4 over x minus 2 minus a 1/4 over x plus 2 dx. Factoring out that 1/4 seems like natural choice, so let's factor that out. So we get negative pi over 2 integral. We'll just write this down. Probably could have just integrated on that step, but we'll just wait. Natural log absolute x minus 2 minus natural log absolute x plus 2 on our integration interval 0 to 1. Okay, well, let's go. So plugging in the positive 1 first. We see that we get a 0 here. Plug in positive 1. 1 minus 2 is negative 1. Absolute value of negative 1 is positive 1. Natural log of 1 is 0. So we're going to get 0 minus natural log of 3. That's the upper. Minus the lower at 0. Plug in 0 here. We get natural log of 2. Distribute the minus to make that plus. Natural log of 2. Oh yeah, so 0 is giving us 0 after all. Didn't notice that ahead of time. So those cancel. So we will end up, final volume will be pi natural log of 3 divided by 2. Yeah, it's nice the board's not turning green and cutting out anymore. Even though it only takes like 5 seconds, it's so distracting. All right, any part of that you have a question on? Everyone remembering disc method? Cross section is a disc, so the area of the disc, if we integrate area, we get volume. All good? All good in the method? All right, well, we might as well stop. We only have 30 seconds. If you have questions, linger, and we can do questions. Yeah, let me hit stop on that recording. And on Thursday, definitely read ahead. Improper integration is the gateway integral to infinite series. So get hooked on improper integration because it's going to lead to infinite series, which are, one of the cooler topics in all of calculus. So read ahead. Read ahead.